Hello dear students, hope all of you are fine. Welcome to YouTube channel of Unique World Education. This is Faslur Rahman, Chemistry Faculty of Unique World Education. So today we are going to discuss a very important physical chemistry chapter from grade 11, that is thermodynamics. I hope all of you know thermodynamics is a very important chapter which is a mark determining chapter for your NEET exam, JEE exam and for board exam also. Okay, so it's a very important chapter from which you can expect many questions for your exams. So what we are going to do in this session means we'll list out all the important formulas in this chapter. Okay, so all the important formulas that you need to know from this chapter we'll discuss in this video. Okay, so thermodynamics, as it is a physical chemistry chapter, you have to be very clear with all the equations, all the expressions, all the formulas and all. Okay, so we have many equations in this chapter, so we'll discuss all the equations today. Okay, so we can start. Yes. I hope all of you know about the important terminologies in thermodynamics, like, for example, systems, surroundings, and all. I'm not going to explain all these things. So, we are directly going to discuss about the important expressions in this chapter. Clear? Okay. So, the first thing that is about first law of thermodynamics. Okay, all of you know about first law of thermodynamics. It is just the same definition of law of conservation of energy. Okay, so what is the expression of first law of thermodynamics? I hope all of you know that. That is connecting internal energy and heat and work done, which are very important parameters of thermodynamics. Clear? So the expression is delta U is equal to Q plus W. Delta U is equal to Q plus W. Okay. So what is U? U means internal energy. Internal energy. So delta U means change in internal energy. What is actually internal energy? Internal energy means the total energy content of a system. See, all these words are very important. Total energy content in a system is called internal energy. See, a system will have different types of energy. A system may contain different types of energy. Clear? So, all the types of energy collectively called internal energy. Internal energy. So, internal energy we can't directly measure. So, that's why we are measuring what? Internal energy change in internal energy. Okay, so that is delta U. So delta U is equal to Q. Q means what? Q means heat. So heat absorbed or heat evolved. Heat absorbed or heat evolved, and W is the work done. Okay, so the sign convention related to heat and work done is also very important. So Q can be positive or negative. So Q can be positive or negative. So Q is positive whenever a system absorbs heat. Okay. So Q can be positive when a system is absorbing energy, and Q can be negative when a system is releasing energy. Okay, so that's very important. Then coming to work done. Work done can also be positive and negative. So work done can be positive when work is done on the system. Okay, work done on the system is considered as positive, and work done by the system is considered as negative. So these terms are very important because you will get this particular terms or sentences in your question paper. Okay, so this is the expression for first law of thermodynamics. This is the expression for first law of thermodynamics. That means the total energy in a system is conserved. Okay, so that will change only by absorbing or releasing heat or by work done. Okay, by doing work by the system or work is done on the system. Okay, so that is first law of thermodynamics. I think the expression is clear. Okay, yes. So next one, yes. Next we can discuss about enthalpy. Enthalpy is a very important part of this chapter. Enthalpy enthalpy is the core part of thermodynamics. Enthalpy, you can expect many questions related to enthalpy and enthalpy change calculations. Clear? So enthalpy is denoted by the letter H. And what do you mean by enthalpy? Enthalpy is actually, that is more related to energy, but exactly it is total heat content of a system. Total heat content of a system. Total heat content of a system. So it's very important. Internal energy is the total energy content of a system, and enthalpy is the total heat content of a system. Okay. So enthalpy also we can't directly measure, so we will measure only the enthalpy change. Okay, enthalpy change of a system. So the expression, I am going to write the expression here. So delta H is equal to delta U plus P delta V, okay, at constant pressure. So delta H is equal to delta U plus P delta V. So delta H is enthalpy change, delta U internal energy change, and P pressure, delta V change in volume. Okay, so this is at constant pressure. Clear? So this expression is very important. And we have one more expression for enthalpy change, that is for the chemical reactions. Okay. In case of chemical reactions, delta H is equal to delta U plus delta NGRT. Okay. Delta H is equal to delta U plus delta NGRT. So delta H and delta U already we discussed. And what is delta Ng? It's very important related to this chapter and some other chapters like equilibrium. Okay, so I think you know that delta N is the change in number of moles. Change in number of moles, and what this G indicate, that is gaseous. So number of moles of gaseous products minus number of moles of gaseous reactants. Okay, very important. Delta N calculation is very important. So we can take one example. So I hope all of you know about Haber's process. Haber's process is the industrial preparation of ammonia. Okay, so the equation is N2 plus 3H2 gives 2NH3. Okay, this is Haber's process. It's a reversible process which is catalyzed by iron, finely divided iron as a catalyst. So here the delta N will be, so what is the definition? Change in number of moles of gaseous products and reactants. So how many gaseous products are here? How many moles of gaseous products are here? 2 moles, you can see 2 moles of ammonia. And how many moles of reactants are there? 1 mole of N2 and 3 moles of H2. So total 4 moles. Okay. So products, gaseous products minus gaseous reactants. So 2 minus 4, that is minus 2. So delta N is minus 2. You need to consider only gaseous components. Okay, that's the thing. So you can write for this particular process, delta H is equal to delta U, delta N is minus 2, okay, minus 2 RT. So this is the relation between delta H and delta U and temperature for this particular Haber's process. Okay, so I think it's clear, it's very important. Okay, both the formulas are very important for calculation of delta H. Actually, delta H or enthalpy is a state function. All state functions are calculated like delta H is equal to H2 minus H1. That means enthalpy of final minus enthalpy of initial state. Okay, but we have certain specific formulas like this. Clear? So calculation of enthalpy change is very important. I'll tell you how to calculate enthalpy changes in a reaction. Okay. So these are the equations, expressions you have to study for enthalpy change. Okay. Then there are different terms of enthalpy. Okay, like for example, enthalpy of formation, enthalpy of sublimation, enthalpy of combustion, enthalpy of neutralization, bond enthalpy, like that many enthalpy related terms are there. So we'll discuss all this in a different session. So in this session, we are discussing about the formulas only the expressions. Okay. So we discussed three expressions. Delta U is equal to delta Q plus W, delta U is equal to Q plus W, then delta H is equal to delta U plus P delta V, and delta H is equal to delta U plus delta NGRT. Okay. Now we have some other expressions for delta H and delta U. That means delta U or internal energy change can be expressed as or can be defined as heat absorbed at constant volume, heat absorbed at constant volume, heat absorbed at a constant volume. Heat absorbed, what is the term for heat? Q. Okay, so heat absorbed at a constant volume means that is QV. Okay, and we have one important expression for heat. That is Q is equal to C into delta T. Okay, Q is equal to C into delta T. So what is Q? Q means heat absorbed or heat released. Okay, so heat change involved. So C is very important. C is heat capacity. Okay, C is heat capacity. So delta T, what is delta T? Delta T means change in temperature. Okay, so from this expression you can write expression for C also. C is equal to Q by delta T. So C means that is heat capacity. Okay, so we have two different terms for heat capacity. So actually what is heat capacity? Heat capacity means that is the amount of heat energy you need to supply to rise the temperature of a substance by 1 unit temperature, okay, or 1 degree Celsius or 1 Kelvin. Okay, so the amount of heat energy required to rise the temperature of a substance by 1 degree Celsius or 1 Kelvin, that is heat capacity. Clear? So we have two important terms, that is specific heat capacity and molar heat capacity. So specific heat capacity, that is for 1 gram. That means amount of heat required to rise the temperature of 1 gram of a substance by 1 degree Celsius. And molar heat capacity, this is specific heat capacity. Molar heat capacity, that is for 1 mole. That means amount of heat energy required to rise the temperature of 1 mole of a substance by 1 degree Celsius. Clear? So you can write like C is equal to Q by N delta T. Okay, for molar heat capacity. And for specific heat capacity, that will become C is equal to Q by M delta T. That means mass. N means number of moles, M means mass. Okay, so this is the expression for heat. That means Q, that is directly proportional to difference in temperature. Delta T means difference in temperature. Okay, so this is one important expression, and this is the expression for what? Heat capacity. From this, we can relate to this equation. Okay, so we have delta U is equal to QV. This is very important. Delta U is equal to QV. So what is Q? Q means C delta T. Okay, or you can say NC delta T. Okay, so heat absorbed at a constant volume. Constant volume. So how you can write delta U is equal to NCV delta T. NCV delta T. So NCV, what is CV? CV means, just wait. Yeah. So delta U is equal to QV. So delta U is equal to NCV delta T. NCV delta T. CV, what is C? Heat capacity. CV means heat capacity at constant volume. Heat capacity at constant volume. So this is one another expression. I think you got it. It's very important. Delta U is equal to NCV delta T. NCV delta T. Clear? Okay. We have one more another expression like this. That is for delta H. Delta H can be defined as heat absorbed at constant pressure. Heat absorbed at constant pressure. Heat absorbed at a constant pressure. Heat absorbed at a constant pressure, that means QP. QP. Okay. So you can write delta H is equal to QP. So QP, how you can write for QP? QP is equal to NCP delta T. So delta H is equal to NCP delta T. What is CP? CP means heat capacity at a constant pressure. Delta H is enthalpy change and N is number of moles and delta T is change in temperature. Difference in temperature. Okay, that's it. That's it. So these two expressions are very important. So delta for delta U and delta H. Got it? Yes, good. Next one, that is, yeah. So we discussed about the expression for delta H and delta U and Q, heat and heat capacity. Okay? Yes. And next expression is for, that is for work done. Okay? Work done calculation. Work done. So work done, we have mainly two important formulas for work done calculation. That is, first one, in the case of irreversible process. Irreversible process. Work done in irreversible process. Okay. Irreversible process, work done can be calculated by the formula work is equal to minus P external into delta V. Okay, minus P external into delta V. That means P external means external pressure. Okay, external pressure into change in volume. So minus P external into delta V. This is the formula for irreversible process. I mean for work done calculation in irreversible process. Okay. So work done by the system will be always negative. Okay. So that's why it is negative minus P external. Okay. Then change in volume into change in volume. And second one, that is for reversible process. Reversible isothermal, reversible isothermal expansion of an ideal gas. reversible isothermal expansion of an ideal gas. Okay, so isothermal means what? Isothermal means at constant temperature. At constant temperature. In this case, you can use the formula W is equal to minus 2.303 RT. Okay, nRT. nRT log V2 by V1. Okay, V2 by V1. W work done, N number of moles, R universal gas constant, T temperature, V2 final volume, V1 initial volume. Okay, or you can write W is equal to minus 2.303 nRT log P1 by P2. P1 by P2 in terms of pressure. Okay, so pressure and volume are oppositely related, that you know, so that's why the formula is like this. So remember, it is V2 log V2 by V1 or log P1 by P2, not P2 by P1, P1 by P2. Clear? Yes. I hope all of you know about the value of R. It's very important. Value of R is very important. I'm writing the value here. R is equal to, that is universal gas constant. We are applying this value of R in many equations in different chapters. R is equal to 8.314 joule per Kelvin per mole. Joule per Kelvin per mole. 8.314 joule per Kelvin per mole. Okay. Or that is equal to 0.0821 liter atm per Kelvin per mole. Or you can say liter bar per Kelvin per mole. Okay, that's it. So the value of R is very important, or mostly they will give the value of R in the question. So no worries. Clear? Yes. So these are the expressions for calculating work done, okay, in irreversible and reversible isothermal expansion. Okay. And sometimes work done calculation will be asked from graph also, graph. So if a graph is given, you can calculate the work done by measuring the area under the curve, okay, area under PV diagram, area under pressure volume diagram, okay, area under PV graph. Clear? Yes. And now I'll tell you some important occasions where work done will be zero. Okay, work done will be zero. So one case in isochoric process. Isochoric process. Isochoric process means volume will be constant. Okay, isochoric process means a thermodynamic process in which volume remains constant. Volume remains constant. Volume remains constant means what? There is no change in volume. There is no change in volume, or you can say delta V is equal to 0. If delta V is equal to 0, definitely work done will be 0, because our formula, what is our formula? Work done is equal to minus P external into delta V. Okay, so work done will be 0 in isochoric process. Okay, very important. And another case where work done is 0, that is this P external is 0. P external will be 0 in the case of free expansion. Free expansion of a gas. Free expansion of a gas. Free expansion means the gas is freely expanding. There is no external pressure. Okay, or you can say expansion into vacuum. Expansion into vacuum. In this case also, work done will be 0. Okay, work done will be 0. Clear? Yeah. So I think the process is clear. Isochoric process. I think you know the words thermodynamic processes like isothermal, that is at constant temperature. Then isobaric. Isobaric means at constant pressure. Okay. Isochoric at constant volume. And one more important word is there, that is adiabatic. Adiabatic. Adiabatic means there is no heat exchange. That means Q is equal to 0. Okay, Q is equal to 0. And cyclic. Cyclic process means it will start from a particular point and ends at the same point. That means change in internal energy or change in enthalpy, or you can say change in all the state functions will be 0 for cyclic processes. Clear? Yeah. So I think it's clear. Now, there is one important relation between Cp and Cv. Okay, what is Cp and Cv? Cp means heat capacity at constant pressure and Cv heat capacity at constant volume. Okay, so Cp minus Cv is equal to R. Okay, so this is also important. Cp minus Cv is equal to R. R is equal to, R means universal gas constant. Okay, yeah. So we have discussed about many expressions. I think all the expressions are very clear. Now we are moving to the next very important expression, that is Gibbs energy. Okay, Gibbs energy, next important term. Gibbs free energy. Gibbs free energy. Gibbs free energy. Okay. What is Gibbs free energy? This is represented by G. Internal energy, I told you, internal energy is the total energy content of a system. Gibbs energy means this is the energy which is available to do work in a system. Okay? Or energy which is useful to do work. Useful to do work in a system. All the energy which is contained in a system that may not be useful for doing work. So only some part of that energy will be useful to do work. That part of energy is called what? Gibbs energy. Okay. So we have one expression for Gibbs energy change. Gibbs energy change, that is delta G is equal to delta H minus T delta S. Okay, delta G is equal to delta H minus T delta S. Okay, it's very important. And delta G means change in Gibbs energy, delta H change in enthalpy, T temperature, and delta S that we are going to discuss the next term, that is entropy. Okay, so I think this formula is very clear. Okay. Okay. One relation between delta G and equilibrium constant you can take down. Equilibrium constant we'll discuss in equilibrium chapter. Okay. So the relation is delta G is equal to minus 2.303 RT log Kc. Log Kc. Okay, what is Kc? Kc means equilibrium constant. Equilibrium constant. Clear? Yes. So that is delta G. Delta G. So delta G is a very important thing which determines spontaneity and all. I'll tell you. Just wait. Yeah. So coming to the next term, very important term, entropy. Entropy. Entropy is denoted by S. Entropy is the degree of randomness in a system. Degree of randomness or disorderness in a system. Degree of randomness or disorderness in a system. Okay, it's very important. That means a very best example I can say, that is when you compare solid, liquid and gas, which is most ordered? Most ordered is solid, okay, and which is most random? That is gaseous state. So entropy will be highest in gaseous state and least in solid state, okay, like that. So we have one expression for delta S at equilibrium, that is delta S is equal to delta H by T. Okay, delta S is equal to delta H by T. Delta H by T. So where delta S is change in entropy, delta H enthalpy change, and T temperature at equilibrium. Temperature at equilibrium. Okay. Yes. And now I'll tell you one very important part of this chapter, which is criteria for spontaneity. Okay, spontaneity. Criteria for spontaneity. Spontaneity means what? For a reaction to become spontaneous. Spontaneous reaction means that is a reaction which is happening by its own. Okay, without the help of any external agency. That is called spontaneity. A spontaneous reaction. Okay. So spontaneous reactions are actually irreversible reactions, or you can say natural processes, natural reactions. Okay. For a reaction to become spontaneous, there are three important criteria. Okay. First one, that is delta H should be negative. Delta H negative means the reaction should be exothermic in nature. Exothermic, very important. Okay. Then only the reaction can be spontaneous. If it is an endothermic reaction, you should supply energy to the reaction. Okay, it won't happen automatically. And second point, that is delta G also should be negative. Delta G also should be negative because the system will be doing work, so the amount of energy which is useful to do work, that also should be decreasing. Okay. And third factor, very important factor, delta S should be positive. Delta S should be positive means the entropy of the system must increase. Entropy should increase. Okay. So these points are very important. Clear? So delta G should be negative, delta H should be negative, and delta S should be positive. Okay. Delta S should be positive. So these are the criteria for spontaneity. Okay. So I think we discussed almost all the expressions. Okay. Uh, yes. So in entropy, enthalpy, Gibbs energy, work done, then enthalpy change calculations. Okay, all we discussed. Yes. Okay. Now I will give you one more important idea regarding delta H calculation. That means many questions will be there for calculate enthalpy change, okay, in different ways, enthalpy change calculation. So for calculating delta H of a reaction, you can follow three steps. Okay, I mean you can follow this particular technique. Okay, that means if enthalpy, standard enthalpy of formation is given in the question. If standard enthalpy of formation is given in the question, you can calculate the delta H as enthalpy of products minus reactants. Enthalpy of products minus enthalpy of reactants. Okay. And second case, if enthalpy of combustion, standard enthalpy of combustion or bond enthalpy is given. Bond enthalpy is given in the question, you can use which formula? Enthalpy of reactants minus enthalpy of products. Okay, it's very important. Clear? So you can calculate delta H of any equations by following this particular method. Clear? Yes. So we discussed all the important formulas in this chapter. I hope it's clear. So you have to write all the equations in your notebook or in a separate sheet, okay, with particular colors and all, because all the formulas are very, very important. Okay. Now, um, I'll give you some questions, some simple questions to answer for you in comment box. That is, listen. Yeah. Okay. What is the relation between what is the relation between enthalpy change? What is the relation between enthalpy change and internal energy change? Internal energy change for this process. What is the relation between enthalpy change and internal energy change for this particular process? So you can comment your answers in comment box. Okay. So I think we can wind up now. I hope all the formulas are very clear. It's very important for all the exams, for your board exam, okay, for entrance exam, everywhere. Okay. So we'll do problems based on these formulas in one another session. Clear? So we can wind up now. I hope all of you got it. Okay. Okay. Bye. Bye, all. Take care.